Hello, Chem 213 students, and welcome back for this week's lectures on Chapter 21, Alpha Carbon Reactions. And so when we finished last time in Chapter 20, we were talking about carboxylic acids. And before that, in Chapter 19, we were talking about ketones and aldehydes. So we were talking about all carbonyl groups. In this chapter, we're going to talk about the alpha carbon and reactions that the alpha carbon, meaning the carbon right next to the carbonyl carbon. And we're going to see what kinds of reactions that those can undergo. And I have a picture of raspberries here. An important ketone is part of the flavor of raspberries, which is why I chose that. So we use Greek letters as we have used throughout the course to describe the locations of carbon atoms relative to a particular group that we are interested in. In this case, we're interested in the carbonyl group, so what we're going to be calling the alpha carbon is the carbon that is attached directly to the carbon that's involved in the carbonyl carbon double bond to oxygen. So those will be called alpha, the next carbons here will be called beta, and then gamma, and then delta, and so forth. So primarily we're going to be looking for reactions that involve the alpha carbon right next to the carbon in the carbonyl group. So alpha protons are those protons that are attached to the alpha carbon, and so if we're talking about alpha protons here on this acetone here, they would be these protons right here, or these ones, either one. So these are the alpha protons, and as we've seen in the past, when we studied previous reactions way back when we were studying alcohols in Chem 212, we discussed the so-called enol, and that is where you have a double bond that is attached to a carbon that also has an alcohol group on there. And we discussed how in the presence of an acid or a base, we can have a interconversion of a ketone into an enol. And ultimately, we can have a reaction in which we can install a group at the alpha carbon, basically doing an addition reaction on this double bond. And that's going to be the first type of reactions that we're going to cover in this. Also, if you have a particularly strong base, one that is more basic than an alcohol, you can deprotonate the alcohol in the enol and get what's known as an enolate ion. So the reactions that we're going to cover in this chapter will proceed via the enol, like here we have an addition to the enol, or the enolate ion as an intermediate. So in the presence of an acid, a ketone will be in equilibrium with another form called the enol. Essentially, what happens is one of these alpha carbons jumps over to the oxygen, and you end up with the pi bond between these two carbons here, the alpha carbon and the former carbonyl carbon. These are referred to as tautomers of one another. And tautomers meaning that you have a interconversion between the two, and they're in equilibrium with one another. Now, under normal circumstances, if you have a ketone, the ketone form will be 99.99% of the molecules will be in the ketone form. Although it's in equilibrium with the enol will be the equilibrium will favor the ketone significantly, and there will be very little of the enol at any given time. However, the enols can be reactive, and we can use that property to go and perform a reaction, a ketone, and turn it into something else. Now, there are some situations where this equilibrium is different. For example, if you have a diketone here, it's quite easy here for the proton to jump over between these two ketones. You have essentially what amounts to a kind of resonance stabilization. Really, it's not resonance, it's more like the intramolecular hydrogen bonding. So when you have the enol here, the enol form, so this would be, for example, if this proton jumped over here onto this oxygen, we ended up with a carbon-carbon double bond here. In this enol form, you're going to have a hydrogen that's attached to the oxygen, and so of course you're going to have a polar bond here, and so the equilibrium here will, the electrons will be positioned more towards the oxygen, giving it a partial negative charge. The hydrogen will have a partially positive charge, and in this carbon-oxygen double bond, as you know, the oxygen is more electronegative than the carbon, so you get a partially negative charge with the oxygen, partially positive charge over by the carbon, and so you get this alcohol here donating a hydrogen bond and the ketone accepting it. And ultimately that leads to intramolecular hydrogen bonding, which stabilizes the enol. And so you get actually a far greater percentage of the enol at equilibrium in a diketone than the diketone itself. Another example in which equilibrium favors the enol over the ketone is in the case of phenol. So as we've learned in the previous chapters, there is a special stabilization to a resonant a benzene ring here due to aromaticity. And so in the case where there's a pi bond between two carbons here, that completes the aromaticity here, and you get that aromatic stability. So in the case of phenol, you're not going to really see much of an interconversion between the ketone, a potential ketone form, and the phenol form. You're mostly going to get the phenol due to the resonance stabilization of the benzene ring, and the aromatic stability in particular. Now, in the case of the tautomerization, as I said, what's essentially happening is one of these protons is jumping over from the alpha carbon over to the oxygen and the ketone. That eventually produces for you your enol. But the way that this occurs depends on whether this is occurring in an acidic or in a basic solution. So the first step, as we have seen many times here, is going to be the protonation of the carbonyl. And we saw this many, many times over in the previous chapter, that often in an acidic environment, this is what will initiate a reaction of the carbonyl group. By protonating it, you make the carbonyl carbon here even more positive, which makes it attractive towards nucleophiles or for other reactions. So in this case, we have a proton transfer, so this lone pair here goes and grabs this proton and creates a bond with it, and then we have these two electrons left behind, so that just leaves a oxygen with two bonds and two lone pairs, giving it zero formal charge. At that point, we have a resonantly stabilized cation, because here we have a pi bond between two atoms of differing electronegativity, and so we could also draw this as having these electrons both attached to the oxygen atom. And so in this resonant form here, this oxygen has two lone pairs and two bonds, giving it zero formal charge. However, this carbon now, which formerly had 4 bonds and no lone pairs, now has 3 bonds and no lone pairs, so it has a positive formal charge. At this point, we still have water being the solvent here. We can then have the water go here and do a proton transfer, removing the proton from the alpha carbon, and then leaving here these 2 electrons to create a pi bond between these 2 carbon atoms, ultimately giving us the enol. And you can see effectively what happened was a proton was pulled off of the acid, and then that creates water, and then the water comes back and pulls a proton and ultimately creates that double bond in the proton transfer. And so we recover our acid, and that's why we say it's acid catalyzed here. But essentially what's happened is a hydrogen has moved from here, it's no longer there at the end, over to up here, and then we get the carbon-carbon double bond here. Now, under basic conditions, this happens in a different way. We start off with the deprotonation of the alpha carbon. And so if we have a hydroxide base here, notice that we're going to have a double resonance arrow that's pretty even here. And this is because the pKa of as we're going to see, we're going to talk about the acidity of the alpha proton. But the alpha proton has about the same pKa as water. In fact, it's slightly higher. So this equilibrium will actually favor the left side a bit more. But you'll have a little bit of this deprotonation that occurs. And so we got to grab a proton here, and these two electrons are left behind as a lone pair. So that ultimately that will give this, this carbon has two other hydrogens attached, right? They're not shown, but we've got two other hydrogens over here. So those hydrogens are still there. We could draw them in, hydrogen here, hydrogen here. There's 3 bonds here and 1 lone pair. So that's a carbon with a negative formal charge. It's a carbanion. So then we can draw here, what we have here is an allylic lone pair. A lone pair that's allyl to this double bond, 1 space away. And so that's one of our resonance patterns here, the allylic lone pair. We use 2 arrows, putting a pi bond here between these 2 carbons. And then we use a resonance arrow here to put these electrons here, showing them just on the oxygen, giving this oxygen 3 lone pairs and 1 bond. So it has a -1 formal charge. Finally, we recover the base because we say this is base catalyzed, right? So the base has to come back in the end, and we recover the base by then protonating by a proton transfer here with the enolate ion and grabbing a proton, and then that ultimately leaves this hydroxyl group with the oxygen with 3 lone pairs and 1 bond. So it has a negative charge. It's a hydroxide. And then we have the enol. So essentially, again, what happened was the hydrogen was pulled off here at the alpha carbon, and then the hydrogen was put on over here. And so you can think of it as a moving of the proton from the alpha carbon up to where the oxygen is, making an alcohol and then leaving a carbon-carbon double bond there. Now, it is safe to assume that we're going to have some fraction of the ketone aldehyde in solution, and an enol will form. So when we have these, we'll have some amount of enol. The alpha position then is thus nucleophilic. So we can draw this essentially as a resonance structure in the enol form. So when we look here, here we have an allylic lone pair. And so we can do the 2 arrows here where we put the pi bond between the oxygen and the carbon, and then this is just the reverse of the last step here or the middle step here that we did in the base catalyzed tautomerism that we showed. And this gives us here this negative charge here, negative formal charge on the carbon. And when we look at the electron potential map, we can see that although you might not expect it in this resonance form, when you draw the other resonance form, you expect that around the carbon here, you're going to have some electron density. And so that's signified here by the red parts, the green parts being neutral electron density, the positive parts here by the oxygen representing a lack of electron density. And so we can see that this carbon is more electron rich in an enol than we would otherwise expect for just a alpha carbon and an alcohol, for example, would have very much less electron density. So it's safe to assume that some of this form will exist when we're in the enol form, and so this gives us this kind of a rich electron density here over by the alpha carbon. So if we have a stronger base, we can form an enolate ion. So here, notice notice the difference between enolate ion and what we have here. So this is an enol. We have another structure here, the resonance structure, that we can show that has the positive formal charge on the oxygen and the negative formal charge on the carbon. However, if we have a base that can deprotonate this very significantly at the alpha carbon with a really strong base, we can really favor a deprotonated enolate ion. So notice the difference here. There's no proton attached to the oxygen here in this case. We just have a deprotonation, so the base pulls off the proton. That leaves this carbon now with 3 bonds and 1 lone pair, giving it a negative formal charge. And at that point we have this allylic lone pair, so we can draw a resonance structure here where we do our 2 arrows for our allylic lone pair, creating the pi bond here. and then putting these electrons here that are in this carbonyl bond, displaying them here on the oxygen. Right, and so we get this this negative charge that's resonantly stabilized and distributed across the carbon here, the two carbons in the oxygen. So the enolate is much more nucleophilic than the enol because it has a completely negative charge, and so this can do a lot of things. It can behave as a nucleophile. It's negative, right? And so that we know that the strongest nucleophiles are negative. We know that going back even to chapter 12, right? Most of the best nucleophiles are negative. So this makes it a good nucleophile. So if we have some kind of electrophile, then we can have a nucleophilic attack on the electrophile. And this can be, we discussed a lot of different electrophiles when we talked about, when we were going through, like, for example, the electrophilic aromatic substitution, right? We can have a wide variety of electrophiles. They'll either be positive or in some way be able to accept a pair of electrons to make a bond. And so we can have two situations here because there's two resonance structures. When the negative formal charge here is described as being on the carbon, that carbon can go and attack the electrophile, and then the electrophile will attach itself to the carbon. Alternatively, with the other resonance structure where the negative charge is on the oxygen, the nucleophile can attack here. The enolate nucleophile can attack the electrophile, and then the electrophile will be installed on the oxygen. Now, we're going to see here as we move forward that enolates will generally undergo the carbon attack, and this can be drawn in one of two ways, depending on which form of the enolate is started with here. So if we start with the enolate form with the negative charge on the oxygen, we kind of show it going backwards and creating the carbonyl bond here again, which essentially puts the negative, if we were doing resonance structures, we put the negative charge here and then it would attack. So we can, this is kind of a shortcut in drawing it, in that instead of, doing this and then going and drawing the other form with the negative formal charge on the carbon and then, doing this, we can do this all in one shot essentially by, instead of writing this arrow, just write an arrow straight from the pi bond here to the electrophile. Install the electrophile at the alpha carbon. Alternatively, if we're starting with this form here already right here, then it's pretty obvious that we just draw the electrons from the the carbanion here going straight to the electrophile. Either of these arrow pushing patterns will be used in the mechanisms shown in this chapter. And so just note that the one on the left here is kind of a shortcut for showing resonance arrows to go to the negative carbon form here and then do the electrophilic attack. Now, when it comes to which protons are going to be involved here, it's going to be the alpha protons, and those are also considered, those are more acidic because because we have this this interconversion between the enols, or if we deprotonate here, as we saw with the enolate ion, we get resonance stabilization. We have these going back here. If we deprotonate this alpha carbon, we have this enolate ion, which is resonantly stabilized. So because of that resonance stabilization of the conjugate base, that makes these alpha protons significantly more acidic. But the other protons, like the ones on the beta and the gamma carbon, would not produce a resonantly stabilized enolate ion. So those are not particularly acidic. So remember, going back to chapter 3, talking about REO, the way we evaluate the strength of an acid is by looking at its conjugate base and seeing how well it stabilizes the negative charge. And by removing these protons, we get an enolate ion that stabilizes the negative charge. Removing these protons does not give us that. So these protons tend to be, at the alpha carbon to a carbonyl, tend to be significantly more acidic than than other protons in the hydrocarbon chain. The beta and gamma carbons are not acidic, really. You'd have to have an extremely strong base to remove them. So just taking a quantitative look at the acidity of these protons at the alpha carbon, what we'll see here is that if we have, for example, acetone here, the pKa for its alpha proton here will be 19.2. Just remember as a comparison, the proton for water here, if we have water, its pKa is 15.7. So these are all less acidic than water here. However, they are much more acidic than any other protons that are attached to carbon. So even if we had, remember, a triple bond on the other end, if we have a carbon-carbon triple bond, this proton here would have a pKa of about 25. And so these tend to be somewhere in between. They're not as weak acids as those protons that are attached to a carbon atom, other carbon atoms, but they're not quite as acidic as those attached to an oxygen atom. They're somewhere in between. So if we deprotonate the acetone here, we'd get we'd get the electrons here. So we have a base here, deprotonates, grabs a proton, leaves these electrons here on the acetone, which forms our resonantly stabilized enolate ion. If we have acidophenone here, this alpha carbon will, or alpha proton will be even more acidic, because not only will it be resonantly stabilized there, we have the benzene ring as well, although it's not resonant throughout the ring here. And finally, if we have acetaldehyde, so the difference here is there's no carbon here on the other side. We have an even more acidic proton here, also a stabilized enolate ion. So one thing to think about, though, is that when it comes to alcohols, those alcohols tend to occupy the same type of region of pKa's here. And so if we want to deprotonate one of these alpha hydrogens, alpha protons, on a carbonyl, we're going to generally prefer a stronger base than most alcohols. So as I said, the pKa for water is about 15.7. For alcohols, it's slightly higher. So these are slightly less, these are slightly less acidic than water. However, they're more acidic than most alpha protons. And so if we use an ethoxide ion, for example, any alkoxide ion, to perform the deprotonation, this is not going to give us a significant quantity of the enolate ion. So here we can see the difference in the pKa's between the formaldehyde here and the ethanol, and we can see that the ethanol is slightly more acidic by about almost 1 pKa unit. So we expect at equilibrium, the equilibrium here is going to favor the left side, and we'll have 10 times more of these reactants approximately than we do of the enolate ion. So when the alkoxide ion is used to react with the ketone, we have a significant equilibrium here that does not really favor the formation of the enolate ion, although some will be present. If we want to irreversibly form the enolate ion, we're going to want to use a much stronger base. And so you're aware that the stronger bases that we've been using to deprotonate things like when we wanted to deprotonate a triple bond, we did not try, when we want to take this proton, our base that we use was not going to be something like an alkoxide ion like we saw before. Instead, it's going to be something like hydride or amide, right? In the case of the alkyne chapter, we very generally used amide. So if we have hydride ion, like sodium hydride, that will grab the proton here, and you will leave the enolate ion. And what drives this reaction forward even further is that this is going to make H2, which will generally leave our reaction vessel. And so Here, this would be plus H2, but the H2 floats away, and so that drives this reaction forward. We can also use, like sodium amide is what we used in the case of the alkynes to deprotonate them. When it comes to enolates, another base that is similar is used, so it's called LDA, lithium diisopropylamide. And so here, essentially, it's going to be like amide, but if it were amide, sodium amide, these two would be hydrogen atoms, right? So instead, they're isopropyl groups. However, we still have a nitrogen here with two lone pairs and two bonds. So that gives it a -1 formal charge, and the lithium has a +1 formal charge. So this makes a stable ionic compound. And so for practical purposes, a compound like this could be useful as a base rather than amide, this larger ionic compound. So it's made here by treating lithium lithium butyl, the butyl ion from the lithium butylide, and we're going to then deprotonate the diisopropylamine, leaving it with two lone pairs and two isopropyl groups here. N-butyl lithium, yeah. That's the common name, but yes, we can call it like that too. Okay, and so essentially this is going to work just like an amide. So when we were doing this in the alkyne chapter, we used amide here, right? And it was a similar thing. We deprotonated and so forth. So this is again going to be analogous, except instead it's just with LDA. You have two isopropyl groups. But likewise here, we're going to have a grabbing of the proton and a leaving of this lone pair, forming our enolate ion. And notice, with amide, the pKa is 38. With this, it's 36. So we're talking, or with ammonia, I'm sorry, the pKa is 38. With the diisopropylamine, here the pKa is 36. Very, 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 not acidic at all. So the enolate ion is much more acidic. And remember that these reactions are going to go from the stronger acid and stronger base to the weaker acid and weaker base. The stronger acid gets to give up its proton and proceed in the reaction. This one is the weaker acid. It's not going to give up its proton. So this reaction will go to the right very strongly, and we'll get many millions of times more of billions and trillions, even let's see, 10 to the 10th power or more of our enolate ion than our ketone or aldehyde here. The isopropyl groups, the purpose of these is when we have the amide here, this behaves as a strong base, but it can also behave as a nucleophile. But in the case of the LDA, it's a strong base, but it's not a good nucleophile, and we want that because remember, with the when we were using sodium amide with the acetylene, the alkynes. We didn't have to worry about a nucleophilic attack, but in the case of the carbonyls, we do, because we've been studying tons of reactions where we have a nucleophilic attack. So some nucleophile comes in here and attacks right here, right? So we don't want something that's a good nucleophile that can easily get in there and attack. And so the fact that we have these big bulky groups on here makes it more difficult to attack as a nucleophile and more likely to behave as a base instead. So when we have protons here that are alpha to 2 carbonyl groups, this makes them even more acidic. This is because we have even further resonance stabilization once the proton is removed. So if we have some base here that removes one of these protons like this is going to leave the lone pair here on the center carbon between these 2 carbonyl groups. And this carbon now will have 3 bonds, 1 to hydrogen, 2 to carbon, and 1 lone pair, giving it a -1 formal charge. So in this case, not only can it is it allyl to the double bond here on the left, but it's also allyl to the double bond on the right. And so you get 2 other resonance forms here, and you'll notice that I went both directions at once here. Of course, you can't do both directions at once. the other way that you could show this is you can go this direction like I've shown here, and we put the lone pair here on the oxygen, and now we just show the reversal of that to undo what we just did essentially, and simultaneously put those electrons over here instead, and then they go over here. So if you wanted to go directly to that, you could just follow these red arrows. If we started here and we use the red arrows like this instead of the blue ones, you'll get to that one. So the shortcut here is just to undo what we just did here and then go and make the other resonance form. So that's a little bit of arrow pushing shortcut there for resonance arrows that's being shown. But the take-home message is that we get we have even more resonance, and so this conjugate base is even more resonantly stabilized, meaning the acid here that loses the proton to create that base is that proton is even more acidic. It's significantly more acidic as the proton that's on formaldehyde here. So what this means is that if you have a diketone like this with the alpha carbon here between both of the ketone groups, you can, because this is pKa9, you can deprotonate this with an ethoxide ion. And so this deprotonation will work just fine. Of course, there's another hydrogen here not drawn, but you'll end up with this highly stabilized ion here, highly resonantly stabilized, which is what gives rise to this pKa of 9. And that is a much stronger acid here than the ethanol. So this reaction would go forward very, very significantly and produce, 10 to the 6 times more of this enolate ion than the diketone that we had at the beginning. So it's important to keep in mind what base that you want to use to generate the enolate ion, because as we said before, a lot of our reactions in this chapter are going to involve the enolate ion as an intermediate. And so if you have just a standard ketone here, remember that sodium hydroxide or some alkoxide ion will not be basic enough to irreversibly form the enolate ion. So we're going to get some of the enolate ion, but we're going to have some significant amount of the unreacted ketone remaining at equilibrium. If we want to irreversibly deprotonate the ketone, we're going to want to use a very strong acid such as sodium hydride or LDA. And remember, we're not using, we might think, oh, what about sodium amide? Wouldn't that work? Yeah, like it did for the alkynes. Remember, it would, but it could also behave as a nucleophile, and we don't want to have to worry about that. And so that's what the LDA does for us. And we'll just get the enolate ion. If we have a 1,3-diketone, then we can use any base. We don't need to use a super strong base like sodium hydride or LDA. We can use sodium hydroxide or sodium ethoxide, methoxide, so forth. And we'll get nearly complete conversion to the enolate. So now we're going to start to talk about the kinds of reactions that can be that these ketones can undergo when they're in the enol form or when an enolate ion is formed. So we're going to start with the formation of an enol. So remember, the acid can catalyze the formation of an enol, and that essentially creates for us a carbon-carbon double bond like we'd have in alkenes. And so those carbon-carbon double bonds can now undergo addition reactions like we've seen in the alkene chapter, chapter 8. And so just a reminder of the way these work. First of all, with the acid catalyzation, we're going to, and by the way, this will work with chlorine, bromine, iodine. It won't work with fluorine. And the reason why, again, is because for each of these, we're going to have to break the bond here. And although the fluorine bond is weak, it's not very polarizable. So this all depends on the ability of electrons to move from one side to the other and to at one point be on just randomly on one side more than the other. And in fluorine, it's so small that that doesn't really happen. So its polarizability is the term we use, is too small for this. So, whoops. So it will just be chlorine, bromine, iodine that can do this. So because we have acidic conditions, this means that an enol is going to be a reactive intermediate. So the first step is going to be the formation of the enol. And so again, just going back to the formation of the enol here, remember essentially it's a jumping of the proton from the alpha carbon over to the oxygen. But this starts by the protonation of the oxygen in the carbonyl, which gives us an oxygen with 3 bonds and 1 lone pair, giving it a positive formal charge. Now, at this point, we also have resonance structures, right? We have a pi bond between 2 atoms of differing electronegativity, so we could also draw these electrons here on the oxygen, giving it 2 lone pairs and 2 bonds, 0 formal charge. But now this carbon here has 3 bonds and no lone pairs, so it has a positive 1 formal charge. And this is the point at which if we deprotonate here, we produce the pi bond. So remember when we deprotonate, this is acid catalyzed, so we have to recover the acid. And so we're going to grab the alpha proton, and then the 2 electrons in the bond between the carbon and the hydrogen become the pi electrons in our double bond. And now this is a alkene. It's an enol, but this is like an alkene, and this can undergo the kinds of reactions that alkenes undergo. So remember that we had a reaction here where we would halogenate, and we'd end up with this this situation where we had a polarizability of the bromine, giving it a partially positive charge here for just a moment and a partially negative charge over here on this side, just by random chance and by approach of these negative electrons in the pi bond, which kind of pushes the electrons away. And then at that point, this bromine can behave as the electrophile and the pi bond as the nucleophile, and we can have a nucleophilic attack on the bromine. And that's exactly what occurs here. However, simultaneously, we can draw a resonance arrow here between the oxygen and the carbon. So when this occurs and the enol attacks the bromine, and then we have a breaking of the bond to the bromine, simultaneously, we have a carbocation being formed here, and it doesn't really, we can draw a resonance arrow here between a lone pair here that is adjacent to a carbocation, and then we'd have the oxygen again with a double bond here and 2 lone pairs. A double bond and a single bond to hydrogen and 1 lone pair. And so that gives it a positive formal charge. At that point, the last step is to deprotonate this. So water comes along, water being the solvent here in all of this, and grabs the proton and leaves the 2 electrons behind. And at that point, we have essentially replaced the alpha hydrogen with a halogen atom. And that's the halogenation of the enol at the alpha position. Now, when we have, so you saw that this ketone was symmetrical, meaning that it had, when we look at the original ketone without the halogen, it was the same on either side of the ketone. Now, it is possible to do this with unsymmetrical ketones. And when we do, notice that, we're getting a positive formal charge in here. We're also making a double bond, and the more substituted double bonds tend to be the more stable ones and produce more a greater product here. Since they're more stable, we'll get more of that product. So when you have an unsymmetrical ketone and you're installing a halogen at the alpha position, it's going to go towards the more substituted carbon rather than the less substituted carbon. Because again, remember, this is going through an enol intermediate, and so this all starts by the protonation of the carbonyl group here. And so we have these lone pairs on the oxygen here. I'll draw them in, and we can have the protonation here, and then we leave these 2 here, and so that's going to give us this protonated carbonyl with a positive formal charge. And at this point, we can, just like we did in the last slide, we can draw the resonance arrow here going to the the oxygen, which gives us the positive formal charge here on the carbon. So now this is an alcohol. It has 2 lone pairs and the positive formal charges on the carbon. At that point, if we have the deprotonation, which hydrogen is going to be removed? We've got either the hydrogen here, or we have one of the hydrogens here. Now, as we've seen before, we're going to, in most cases, we're going to get the formation of the more substituted product, or we called the Zaitsev product at one time. And so the deprotonation will happen here instead, and we'll end up with a double bond that's going to be right there. The more substituted, which is more stable, rather than the less substituted. So we don't get the deprotonation on this side. So we're going to have the more substituted enol will be the major product, and the minor product will, or the halogenation at the more substituted alpha carbon here will be the major product, and the halogenation at the less substituted alpha carbon will be the minor product. So this alpha halogenation, it provides a 2-step synthesis also for the formation of an alpha beta unsaturated ketone. So what we do is, we do this first step, and at the end of the first step, what we're going to get is we're going to get this alpha halogenated ketone. And at that point, if we have a base, we can do an elimination here, and that elimination, so in this case, the base being pyridine. Remember pyridine, this is an important structure to remember, its common name. In fact, pyridine is this one, behaves as a great base because it has these localized 2 electrons that are not a part of the resonance. They're in the unhybridized, or in the hybridized sp2 orbital. But essentially what we can do here is have a deprotonation and an E2 mechanism. So E2, we have the deprotonation here, we have the formation of the pi bond and the simultaneous loss of the bromine leaving group, and that produces for us the double bond right at this position. You can use a variety of bases. Pyridine can be used, so can tert butoxide. Other bases can be used as well. Another reaction here that the mechanism is not completely known. There's some ideas of the mechanism, but it's synthetically useful. It's called the Hell-Volhard-Zielinski reaction. And this brominates the alpha carbon of a carboxylic acid. So essentially what occurs is at the alpha carbon here in the carboxylic acid, we get a bromine atom installed. Okay, this mechanism is believed to follow the following sequence. So we treat with PBr3, and we remember from chapter 20 that the treatment with PBr3 involves the installation here of, we did this also with chlorine here, with the SOCl2. We can get a acid halide here with PBr3 to brominate, or SOCl2 to chlorinate, and we get the acid halide. The acid halide then forms an acid halide enol in equilibrium here. And finally, if we react with Br2, we get a bromination again of the enol at the alpha carbon. And then finally, with treatment with water, will give us the final oxidized product here, where the bromine is then replaced again with the OH group. So the detailed mechanism is not known. I'm not really going to ask you about this, but this is a reaction that could be synthetically useful if you want to put a halogen in the alpha position here on a carboxylic acid. Okay, let's see where we at. All right. So alpha halogenation can also be achieved under basic conditions. So remember that the formation of the enolate is going to involve a different mechanism. With the acid, our mechanism involves the protonation of the carbonyl first. In this case, we're going to have the deprotonation here at the alpha carbon, And remember, this is an equilibrium. The water, this is actually less acidic than the water that's produced. And so we'll get a little bit of this, but that's enough to initiate the halogenation. And so now, in this case, again, we have the situation where we have a polarizable bromine. So at any given moment, maybe there's more electron density here and less over here. That can make it attractive enough to this carbanion that's produced to go and attack as a nucleophilic attack on the bromine, which breaks the bond between the two bromine atoms, and then that gives us our alpha bromination. Notice that in this case that this can only happen on the alpha carbon here because this alpha carbon does not have any hydrogens that can be removed. So the difference here is that before, in the halogenation, the enol was the intermediate, but under basic conditions, the enolate ion is the intermediate in this halogenation. Practically speaking, when we brominate the ketone and it forms an enolate ion, it can brominate again and again. And so poly-halogenation, as we saw in the radical halogenation too, back in chapter 10, in this case, poly-halogenation is very common, and so we might end up with more than one halogen atom attached when we do the base catalyzed halogenation. Another important synthetic reaction here, the methyl ketones here are converted to carboxylic acids in the so-called haloform reaction. And so this involves a treatment with sodium hydroxide and bromine. And again, that's the reaction we just saw. So that produces for us a polybrominated. So let's, at least one bromine, maybe more. And then treatment with acid here, as we saw. That will ultimately get us the carboxylic acid here. And so this is again a kind of partial-ish mechanism here. So we start with like I said here, this first step is the poly-halogenation, and the full mechanism is not completely shown. However, after the full halogenation, treatment with the base here involves a nucleophilic attack on the alpha carbon. So again, remember this here, when we have something that's a good base and a good nucleophile like this, it can attack at the alpha carbon, particularly as this halogenation here, triple halogenation, is really withdrawing electron density from this carbon. So this carbon's becoming really partially positive, being really attractive here to nucleophiles. And then we have the nucleophilic attack and the resonance arrow up to the oxygen. And this CBr3 acts as a good leaving group. And so then we put our resonance arrow back here, putting a pi bond, but this carbon cannot have 5 bonds. So the leaving group leaves here, and ultimately we get the carboxylic acid that returns. And if it's under basic conditions, like for example here, the CBr3 would be a great base. Often this is going to come out in the deprotonated form. The CBr3 that left as the leaving group could then grab the proton here, and then we get bromoform here, CHBr3, and this enolate ion. So if we want to produce carboxylic acids from a ketone under basic conditions, this is a way to do it. So we deprotonate, create the enolate, halogenate this, and then we polyhalogenate, and then finally when we treat with the acid, the halogen leaves as a leaving group, and we get the carboxylic acid. So this is going to be one that you're going to want to keep in mind if you have a ketone and you want to make a carboxylic acid out of it. And it works best if the other, as we saw in our example here, the other alpha carbon doesn't have any hydrogens, because then you're going to get a competition here with reactions on the other alpha carbon. And so that's going to be it for this first lecture of this week. What we've covered here is the enol, the keto-enol tautomerism, the formation of enolate intermediates upon reaction with bases, and a variety of reactions that can be used when this occurs. When we go into the next lecture, we're going to begin to talk about Aldol additions, meaning the addition of a hydroxyl group here over at the beta carbon. And I look forward to seeing you then. Have a good one.